Hi, in this video we'll do an example using iterated integrals, and then we'll talk about calculating integrals over regions that are not rectangular. So I'll leave this one up to you to try. We can compute the integral of the function xy over the rectangular region where x is between 0 and 2 and y is between 1 and 2. Fubini's theorem tells us there are two ways we could set this up. And then if we carefully do either of these, evaluating the inside integral and then the outside, we should get the same answer, which in this case is 3. We'll move on to treat the case where our region R is not a rectangle. So not every region will be rectangular. For example, we might ask the question, what's the area under the surface z equals xy over this triangular region R? So how can we do that? The idea is sort of the same. I will build on some of the work that we've done already. We can break our region R into strips. We can talk about vertical strips or horizontal strips. We'll start with vertical strips. And we'll compute the integral along each of those strips. So if we start, say, with a vertical strip here, you can see, well, the width of this strip, if we call that delta x, you can see that the point at the bottom, maybe we can call x0, so x will just be kind of the horizontal address here, but I hope you see why the y coordinate will be 0. And then if we take this up to the top of the triangle, this will go up to the point x, 2x. The reason for that 2x, this hypotenuse of the triangle lives on the line y equals 2x. So we can talk about the kind of area above that strip. That's an integral of the function f(xy). And the y bounds for that integral are 0 and 2x. And if we wanted to make that a volume calculation instead of an area calculation, we'll add some width to it in the x direction. Well, that width is delta x. And then the strategy would be let that delta x get small, take the volume of all those strips along the triangle, and add them together. And we can ask, well, what's the x address of that very first strip on the left-hand side? Well, that happens at the origin, that's when x is 0. And that very last strip on the right side, well, that happens at this rightmost leg of the triangle when x is 1. And we put it together, and here's an iterated integral that we can solve. So we see those y bounds on the inside that vary depending on the x address, and the x bounds on the outside telling us where we'll find the first and the last of those vertical strips. And we can compute this just like we did the others. We'll apply the fundamental theorem of calculus on the inside. Since dy is on the inside, we're taking the antiderivative with respect to y here, treating x like a constant. And now when we plug in the endpoints, well, the endpoints depend on x. So we'll plug in 2x for y, we'll plug in 0 for y, subtract those just like we do with the fundamental theorem of calculus. And we're left with an integral at this point involving only x. Hopefully we can do this easily. And we'll see that the answer is 1/2. That is the volume under the surface z equals xy over the region of this triangle, 1/2. Now, there's no reason we had to do vertical strips. We could have done the same by drawing horizontal strips, that is, from the hypotenuse of the triangle over to the leg on the right side. We could talk about kind of the coordinates, the address for the endpoints of those strips. In this example, those endpoints should depend on y, right? We'll have wider strips at the bottom of the triangle and shorter strips at the top. So on the right-hand side, the x-coordinate is going to be 1. Well, everything on the right-hand side of the triangle has an x-coordinate of 1. But on the left-hand side, the x-coordinate should be y over 2. And to think about why this is true, remember we said that this line was y equals 2x. Well, that's like saying this line is x is y over 2. So that's where that comes from. And we can do the same. We could say integrating along one of those strips has x bounds from y over 2 over to x equals 1. And then if we wanted to collate all of those strips, we have to start with the very first one, that's at the bottom when y equals 0, up to the very last one, that's at the top when y is 2. And we can write our iterated integral that way. And we don't need to do it. We already know the answer is 1/2. It's good practice. You can try it. And I'll leave you with this last question. Why was the answer not this other integral that I wrote down here, with x bounds going from 0 to 2 and y bounds going from 0 to y over 2? So think about why that's the case. When I see you in class, we'll practice lots of these. It does take some practice, but we'll be experts at it in no time.